Hello, hi everyone. Uh, Welcome to the Temporal Graph Reading Group today. We are glad to host um, Abdulkadir Celikkanat from the Department of Applied Mathematics and Computer Science from um, Technical University of Denmark. And Kadir recently started working as an assistant professor at the Aalborg University, and he was previously a postdoc researcher at the Technical University of Denmark. He obtained his PhD at uh, Central Supélec University of Paris, where he worked on representation learning methods for graph structured data. And before that, he earned his bachelor's in mathematics and a master in computer engineering from the the Bogazici University. And currently, he is interested in the um, metagenomic spinning problem and working on integrating heterogeneous environmental factors with um, bacterial genome data. And he will be presenting the continuous time graph representation with sequential spiral process. And I will leave the mic to you, Kati.
Okay, thanks so much, Andy. So today I will talk about our two continuous time network embedding approaches. And so these works have been done while I was at DTU together with Nicholas Nakis and Martin Moab. So, and in my presentation, firstly, I will give a brief introduction to graph representation learning models. And then I will talk about our first approach, piecewise velocity model. And then later I will describe how can we extend this approach for the networks that we will call as intermediate edge persistent graphs. And later I will finalize my presentation. But please interrupt me whenever you have any questions or if there's anything unclear. So as you know, the graph representation learning models mainly aim to represent every node of the network into a low dimensional space by preserving some structural properties of the network. For instance, here we have two clusters. So we would like to, let's say you might want to have a closed node representations for the nodes belonging to the same cluster. And more formally, we can say that we would like to learn the embeddings of nodes U and V, such that the distance in the embedding space between U and V should be close to the user specified distances. So here, by optimizing this loss function here, L, then we learn the embeddings of nodes U and V, and then these embeddings later can be used to perform some predictive task on the networks like node classification or link prediction. So, and for the continuous time temporal network, so each edge is represented by a triplet, I, J, and T. So I and J indicates this not labels, and T is the timestamp. So in fact, it represents the appearance times of the edges. And similarly, for the continuous time networks, we also would like to learn the embeddings of nodes reflecting these temporal changes in the network architecture. And so in my presentation, I mainly focus on the temporal networks, and we can roughly group these networks as discrete time networks. So in the discrete time temporal networks, these edges or links among nodes occur in discrete time intervals. And for the continuous time temporal networks, we observe the events or nodes in the time point. These links or edges can occur at any point in time. So I will mainly focus on these continuous time temporal networks here. And so we assume that each node pair, I and J, might contain multiple interactions over time. And a typical way to model the number of events occurring in time or the locations in spatial space might be to use a pause and point process. So similarly here, we use this Poisson point process to model this number of interactions between nodes I and j. But we also assume that this linkage pattern between nodes I and j might also change over time. So that's why the intensity or the interaction between nodes might also change over time. And so this intensity parameter here, lambda ij, will also change or depends on time t. So our main goal will be to, let's say, approximate this correct intensity function based on node representation here, R of I and T. So I indicates the node label and T is the timestamp. So we define the intensity function based on some exponential link function here and with some bias terms, beta I and beta J. So, and these parameters are responsible for some non-specific effects like the degree heterogeneity. And here Ri of t indicates the embedding of node I at time t. So for instance, let's say for a given interval, if there are high number of interactions between nodes I and j, then it means lambda should be high. So we should closely position these nodes I and j in the embedding space. So if there's no interaction for a given interval, then lambda should be small. And to make it small, we will position these nodes far away from each other in the embedding space for this time interval. So yes. So, and this Ri of t is a function. So we define it as a linear model with parameters xi and vi. And these parameters also can be thought of as a initial position of node I and its velocity vector. So if we learn these parameters, xi and vi, and for given any time point t, we can compute the position of the node in the latent space. But these formulations provides a limited capacity because nodes cannot do some flexible motions in the embedding space. For instance, let's say in this figure, these nodes I and j, firstly, they have a high interaction period or some interval. So to represent this period, they come close to each other in the latent space. And then later they have no interaction interval. So that's why they have to be far away from each other. And later they have an interactions again. So they have to come to close to each other. But if we have such a linear model, nodes have to go only in one direction because they have only one velocity vector. That's why to increase this nodes, let's say flexibility, we divide the timeline into b equal size bins, and for each bin we introduce additional velocity vector. So that's why for a given, let's say these velocity vectors and the initial position, we can find the exact location of the node at time t. And so here I have some illustrative figure. So the first row indicates this grand root, let's say representations in the latent space. And the second one is this predicted, let's say, trajectories. Here we divide the timeline into 4 bins. So for each bin, we have one velocity vector. So that's why we perform, let's say, piecewise 4 linear motions in the embedding space. And we try to approximate these correct trajectories. And it can be also seen that if we increase this number of bins, then we can nodes might have a more smooth trajectories in the embedding space, and then we can better approximate the correct, let's say, embeddings. So we also suppose that these initial positions and velocities follow the normal distribution with zero mean and the covariance matrix sigma. Here it is also defined as a canonical product of three other matrices. B, C, and D. They are also responsible for this temporal node and dimension-specific covariance structures. So by combining this log likelihood function log likelihood of this non-homogeneous Poisson process, and this is log prior. Then we can define our objective function, and then we can learn the initial position and vertices, and then we can obtain the representations of the nodes in the continuous time space. So we also perform some experiments to evaluate the model's performance. Here we generate, or we have two artificial data sets. The synthetic alpha data sets follows our model's assumptions. So we sample the links from the non-homogeneous Poisson process, and for the second artificial data set, we divide the timeline into 10 beans, and for each bean, we randomly cluster the nodes, and then we randomly add the edges. And we also here we have 5 continuous time networks. So our first task is the network completion, and we know that many real networks might have some noisy or missing links. So it might be important to assess how the models is good at capturing this general linkage structure of the networks. That's why we randomly sample 10% of the diodes in the network, and then we split these diodes to validation and testing sets. Then we train the model on the residual network. So here, LDM and NOTVEC, as you know, they are the static non-emitting methods, and the other ones are the continuous time temporal network, continuous time network embedding approaches. So here we outperform the most of the baselines in terms of the AUC log and the PR scores. And for the future link prediction task, we take these events occurring in the last 10% of the timeline as a testing set, and then we train the model on this initial 90% of the edges. So, as I mentioned before, this synthetic alpha data set follows our model's assumption. That's why our model is good at predicting the links for this network. But for the synthetic beta datasets, it has a completely random network structure, so it's very challenging to make these future link predictions. And also, our model for some real datasets shows sometimes better, sometimes comparable performance also compared to other baselines.
Can I ask a quick question?
Yeah, sure, definitely.
So how does your model like updates its information or embedding at test time? So let's say you have the rest, like you use like 50% of data set as test set instead, and then does your model like can update its embedding with the information you see at test time, like when you
Yeah.
like kind of the test update setting?
So in this model, particularly, we aim to capture this because we have this prior here. And so we aim to, let's say, capture some maybe clustering structure and then temporal, let's say, covariance structures. But it was very hard to optimize this covariance matrix. So that's why our predictions mainly rely on the last state of the embeddings of the training time.
I see. So you're doing basically
Otherwise,
like multi-step prediction. So you're predicting for all the rest with the same embedding.
I can say mostly we sample from this normal distribution again the some velocity vectors
Right.
to predict future if they have future motions.
Mm-hmm.
But it's very hard to for real data set. It was very hard to optimize this covariance matrix. That's why in most of the cases I can say that our predictions rely on this last state of the model.
Right.
at the training time.
Yes, that makes sense. Thanks.
Yeah. Okay, so we also have done some visualization experiments. It might be important for the practitioners who want to understand these underlying mechanisms of the networks. So on the left part, you see the ground truth representations for the artificial data set, and the right one indicates these learned representations. So unfortunately, this problem doesn't have a optimal solution, like unique solution. There might be many optimal solutions, but our model is at least is good at capturing this temporal clustering structure in the network. Oops. So yes, that was the first part, and so our approach, piecewise velocity model, and also many other continuous time networks, mainly only they focus on the event time of the links, but not their persistence. But in many real networks, have this intermediate link structure. For instance, on Twitter, let's say you can follow a user, and maybe 6 months later you can find he doesn't share any useful information, and you can unfollow, and later maybe you can start to follow him again. So these networks, networks have such kind of intermediate linkage structures. So events in the previously events or links indicates these instantaneous event points, but here in this case we will focus on so each edge will have this intermediate linkage structure. For instance, if we consider this pair, here initially they don't have any link, and then during this period they have some interactions here, and so later they don't have any edge here, and then later we have an edge again, and then there's no edge again. So we will call these networks as continuous time intermediate edge persistence graphs. And for this model, we aim to learn knot embeddings for these networks. And for this purpose, we will use these survival functions. And in many disciplines, the key focus on understanding this how long events take to happen. For instance, in studying these lifetime estimations of the living organisms, or in understanding how reliable the mechanical systems are. And so in this field, the term survival is mostly used to describe the duration leading up to the occurrence of death or failure. So similarly, we will use these survival functions to model the appearance of the edge and also disappearance of the edge. And then later, we will model again the appearance of the edge again. So for our model, we will use this survival analysis. And so I'm not diving too much detail about the survival analysis, but we know that survival functions can be reparameterized by using this hazard function, lambda of t prime. So as I mentioned, we use these sequential survival functions to model this edge period, non-edge period, and edge period, and non-edge periods of each node pair. So that's why we propose this sequential survival process. And so it relies on these sequential survival functions. But here we just have additional parameter Sn. So it indicates the state of the node pair at time t prime here. So let's say if there's an edge between these nodes, then it will be +1, otherwise it will be -1. So similarly, we can write the localized function for the whole network based on this sequential survival process. And again, so we similarly define this hazard or intensity function. But so we have again here the global bias terms, and so we have a distance term, but here we have additional term S, so it indicates, as I said, a state of the node pair. Let's say if there's a edge between nodes I and J, so it will be +1. So we need to maximize this lambda. So that's why nodes will be again closely positioned in the embedding space. Otherwise, it will be -1, and then we will try to minimize lambda. So nodes will be positioned far away from each other. Sorry. So and also we can write some lower and upper bounds for the average distance between nodes for a given interval. So we can have some guarantees about this some guarantees about representing the structure, representing the temporal changes in the network in the latent space. So let's say if there is some change in the network architecture, so we will have some guarantee that for lower and upper bounds to reflect these changes in the network architecture in the embedding space. So here we similarly use these piecewise linear motions to define the embedding of the node I at time t. And similarly, we suppose that velocity vectors follows the normal distribution. So we have a similar experimental setup. Again, we generate two artificial networks here, but in this case, links also have some durations. So in the previous time, links only indicate instantaneous event times. So in this case, the real networks and artificial networks also have some durations. And so we also have done some network visualization here. As you see, in this case, links have some duration, so they disappear maybe after a certain time and then maybe reappear again. So our model here is good at capturing this temporal clustering structure in the network. So again, we are doing the similar experiments. Here we just sample 20% of the dyads from this validation and testing sets. And so we have this same static network emitting approaches, LDM and NOTVEC. And we use other continuous time network emitting approaches here. And we also include our previous architecture, PM here. As far as we know, there is no similar architecture which can handle such kind of intermediate edge persistent graphs. So here we outperform the baselines in most of the cases. So for the feature link prediction task, we observed a similar pattern here. If the linkage structure of the networks follows our model's assumptions, then our model shows a good performance. But otherwise, it's very hard to make the predictions if the network doesn't have any recurring linkage pattern. And especially it's very hard to make the predictions for the links that are very far away from this last training time point. Okay, so we also examine the impact of some hyperparameters. So as I mentioned, we have this number of beans. Well, when we increase this number of beans, our model's capacity increases. So for this experiment on the artificial data set, so we increase this number of beans, and then the performance also increases up to a certain point, and then it saturates because the model reaches to enough capacity. And for the dimensions, we similarly, when we increase the dimensions, model's capacity increases. But in these two models, we mainly focus on the very small dimensional embedding space because we also want to have these nice visualizations without needing extra tools like TSNE for the dimension reductions. So as a conclusion, we firstly propose a novel continuous time non-representation learning model accounting for only the event times of the links with this PVM method. And later we propose this sequential survival process, and based on this process, we learn the node representations for this continuous time intermediate edge persistent graphs. And we show that our models can outperform the baselines on different type of data sets. And also we show that our models can be also serve as a visualization tool because we show that our models can accurately embed the networks in very small dimensions like 2 and 3. So yes, that's all. If you visit our project websites, you can also find more details, animations, datasets, and also implementation. And thank you. If you have any question, please let me know.
Yeah, so thanks for the very nice presentation. There are a few questions from the audience.
Yeah,
Uh,
sure.
do you want to ask the question yourself, Junaid, or do you want me to just say here? Feel
Uh,
free to unmute. Yeah.
sorry, I cannot talk. I'm in a different time zone.
Okay, okay. So
And yeah,
yeah, so I will just read off the questions then.
Okay.
So the first question is, why do we have movements in the temporal ground truth representations, or like what does the movement mean?
Yes, because we generate these temporal networks. And let's say we have this ground truth network, and then how we generate it, we firstly sample these initial position and velocities. So, and then based on their positions, we generate the links by sampling from this, let's say, non-homogeneous Poisson process, or for the second model, we sample these links based on the sequential survival process. So
Okay.
since we firstly sample this initial position and velocities, that's why we have this, we know their latent motions.
So the generation is based on the 2D like Euclidean distance that you see in the ground truth representation. Then you generate the edges based on that, basically.
Yeah, here we generate some artificial data set. That's why firstly is sample these embeddings, and based on the embeddings, we sample these links.
Okay, sounds good. The next question is, can you explain the edge duration again, and how does the model handle that information?
Yes. Where is it? Yes. Okay. Normally, in many continuous time network approaches, they only handle this event time of the links. So do you have only just the interactions. And also, so here we suppose that you might have an interaction and then it might have some duration, and then this interaction disappear. And later, for example, like in Facebook, you can become a friend, and maybe 3 months later you can defriend, and then maybe 6 months later you can become a friend with the same person. So that's why we have such kind of durations.
Right.
But yeah. But in many other, let's say, network, like continuous time networks, you have only just one interactions. So each edge indicates an interaction. Like let's say you have some sensors, and then if you two persons are close to each other, then you have just one event.
Yes, I
Yeah.
think that's very interesting, and there's not that many data sets that do have this.
Yeah, exactly. We also had some issues in finding this suitable
So
data
I
set.
think that that's because normally people will just process it into the event-based data sets,
Yeah, exactly.
even though the relations are kind of have a duration, or it's hard to know like exactly when does it end. So it
Yes, exactly. For example, for the Facebook data set, you know that when they become friends, and then most of the time they don't. Yeah, it's hard to know.
they don't show you. Yeah, exactly.
Yeah.
Okay. There's more questions. I'm gonna click this answer live button. I don't know what it does, and see if you can see the question. Oh,
Um,
whoops. Um,
so yeah.
no, I don't think that one works. So it's just the question is just is not using, so is using beans on the continuous time model equal to the discrete time model?
It's not using beans on the continuous time model. Not using beans on the continuous time model. Okay, I think this is some we have these models. We have these beans for our model because as I described here, let me go back. Yes, maybe here. So let's say we need to define, firstly, we would like to have a embeddings in the continuous time space. So the embeddings also change in the continuous time.
Mhm.
Let's say if we use such a linear model, nodes can go in one direction. To have more flexible, let's say, embeddings, or to improve this nodes flexibility in the embedding space. That's why we divide the timeline like here. So let's say if we divide the timeline into 4 bins, and then for each bin interval, then here we will have a, let's say, one linear model. And then if we increase this number of bins, we will have a more smooth trajectories.
Mhm.
So that's the idea of why we have these bins.
Yeah.
But I didn't understand the discrete time model.
The discrete time is just like snapshot-based models. So
Yeah, discrete time, just you have a, I think I couldn't figure out the connection between the bins of the model and the discrete time networks. In the discrete time networks, we observe the links at fixed intervals.
yeah, so I think the question is really about the within a bean, if you collapse the edges, it's as if it's a discretized model.
Yes, but in that case, you won't have a continuous time representation. You don't need a
Yeah, so the
continuous time.
representation itself is different. Yeah.
Yeah,
And the way you do query is different.
yes.
So the last question is, what is the time complexity for your model?
Okay, for time complexity, we also in the paper, I don't remember the exact time complexity, but we also provide this detailed time complexity analysis in the paper.
Mhm.
So we are, for the training, we are also doing the batching. So it depends on this number of nodes and number of interactions
Mhm.
and size of the batch and dimensionality, since we have work on very small dimensions.
Right.
Yeah, like, and also it depends on the number of beans. If you have a high number of beans, then the complexity definitely increases. But we also, in the experiments, we observed that 100 beans, in most of the cases, it works well. So
Okay.
you don't need a very large bean number.
So basically some constant times node and number of nodes times number of edges, because compared to number of nodes and edges, the batch.
Yeah, something like this. Yeah, exactly. I don't remember, but I need to check the paper to see all these derivations.
Okay.
Yeah.
Cool. Yeah, so thanks for the answer and the presentation. So I think Junit's question has been answered. So
Okay.
so let's thank the presenter again for the very nice presentation and nice visualization. I think it's a very interesting direction, and I think like hopefully we get more data sets in this domain as well, because
Yeah, definitely. Hopefully. And then, yeah, if you have any other questions later, you can contact me, and then, or you can check this project websites just here. Yes.
great.
Yeah, thanks so much also
Yeah.
for
Thank you.
listening.
Yeah.
Thank you.
Have a nice week, and see
And
you
you
guys
too.
next week. Thank you for
Yeah.
presenting. Bye.
Bye bye.